In this short video, I'd like to take a brief look at different types of synthesis. I'm gonna start with subtractive synthesis, as it's easy to compare different types of synthesis to it. Okay, so let's start from the left, where the first synthesis block is located.
The oscillators.
The oscillators are generating raw waveforms. Let's listen to some of them. So the first oscillator offers noise. As you can see, it doesn't matter which key I press because noise is a random signal with no pitch. Saw wave. The next one, a square wave with this slider allows us to mix between two oscillators. The oscillator 2 is much like the first one, but it offers a triangle wave instead of a noise. So let's have a listen to it. And additionally, the second oscillator can be detuned from the first one. So if you listen to two of them, play a note and detune, we'll hear the beating.
Synthesizer, synthesizers.
The next element in the synthesis path is a filter. This graph here represents volume on its y-axis and frequency on its x. When we close the filter, some of the harmonic content will go away. Let's have a listen to that. You can clearly hear how the filter affects the sound. Now let's have a listen how high frequencies are being filtered from the sawtooth wave. This is a low-pass filter. It filters the frequencies above a specified cutoff frequency, letting all the low frequencies to pass through the filter. There are some other types of filter. For instance, we can choose a high-pass filter, which is just opposite. It cuts the base frequencies below the cutoff point and lets all the high frequencies to go through. Let's have a listen to this. Three other common types of filter are bandpass filter, which only lets some frequencies around the cutoff point to pass through the circuit, and a band resistant filter, which is opposite to bandpass. It only filters the frequencies around the cutoff point. Another important parameter of the filter is its resonance, which allows us to boost the frequency at the cutoff point. At a very high level of resonance, the filters start to self-oscillate.
Synthesizers with synthesizer.
We can make our sounds to change over time by using modulation. The two most common modulation sources are LFOs and envelopes. To demonstrate that, I'll turn up an LFO knob in the filter section to make the LFO affect the filter. An envelope, unlike an LFO, which produces a constantly repeating waveform, produces a control signal sequence only once after it's triggered by a node. It allows us to set usually 4 relative levels, which are attack, decay, sustain, and release. To demonstrate different stages of an envelope, I'll use an amplifier envelope, which controls the whole signal that is coming out of the synthesizer. And now I'll increase the first parameter, which is attack. So the first stage defines how long it will take to reach the maximum level from the moment when the MIDI note is played. As you can hear, it takes 10 seconds now, and now signal is at the maximum level immediately after I trigger the note. Now we have very short decay, and I'll keep playing the notes while increasing decay time. The next parameter is sustain, which defines how loud the sustain of the note is in relation to its loudest part. So you can hear that the signal goes up and then the level drops down. And the very last parameter is release. It says how long it will take the signal to fade out after the MIDI note is released. If we set it to 0, the signal goes away immediately after I release the key. But if we make it longer, we can also use filter envelope in the same way as we use amplifier envelope, and we can adjust the way it affects the filter by this knob here. So let's have a listen to a short decay time on the envelope of the filter. And now let's increase the attack, which will produce a nice sweep. Next type of synthesis is FM synthesis, which stands for frequency modulation synthesis. So as the FM synthesis is the type of synthesis which is actually quite different from subtractive synthesis, especially when it comes to pure FM synthesis of early FM synths. Here is a quick explanation of the 4 most important terms which are associated with it. First, operators. This is how wave generators at the beginning of the synthesis path are called in frequency modulation synthesis. Basically, the oscillators in FM synthesis are called operators. Every operator falls into one of 2 groups. It can be either a modulator, which is an operator that is not heard from the output of the synthesizer, but its signal is used to modulate the sound of another operator, which is called the carrier. And the carrier is the operator that we can actually hear from the output of the synthesizer. The last term is the algorithm. The FM synths are likely to offer different ways of connecting the operators together in order to be able to produce a wider range of sounds. The way in which the operators are routed and connected together is called an algorithm. Here we have the carrier and the modulator. Let's put the carrier to the first harmonic and then the modulator to the second one. Let's now increase the FM knob to turn up the amount of frequency modulations. We have a nice Rhodes synth sound. Because the carrier and modulator are in a consonant relation, we have first and the second harmonic. Let's see what happens if we set the carrier to the second harmonic and the modulator, for instance, to seventh. Just as expected, we have that bell metallic sound because the carrier and the modulator are in a dissonant harmonic relation. The more we detune the modulator from the carrier, the more inharmonic content we're going to produce. Next type of synthesis we're going to take a look at is wavetable synthesis. So let's hit the table button here to turn the retrosynth into a wavetable mode. And let's listen to some of the wavetables. You can also choose the starting position of the wave. The last synthesis type is physical modeling synthesis. And here again, we have the filter, we have really advanced modulation possibilities, effects, and many different options. But when we go back to the first block of synthesis, instead of oscillators, we have a physical modeling section. So this particular synth emulates behavior of a string, which is represented by this string here. When I play the note, it visually represents the behavior of the string. What we can do, we can adjust the position of the pickups, which are collecting sound of the string. We can choose up to 3 independent objects to trigger the string. We can also change the material of which the string is made. Let's set it to nylon for now and have a listen to how different objects produce different sounds. So the first type of object is impulse. You can change it to strike. Not very different, but when you change it to bow, give the sound of the bow string and blow. In this section of the video, I'm going to take a look at sampling and try to create a multi-sample patch. But before we start, here's some basic sampling terminology explained. A sample is an audio file that we put into sampler to create sounds.
The process of recording in this case is often referred to as sampling. A sample patch. A sample patch is the set of settings for the sampler that is telling the sampler how to treat an audio sample. It doesn't contain samples, it doesn't contain any audio data, but just the settings. So you need to make sure to save both your patch and your samples in order to be able to use it on a different setup. Playback mode. All samplers offer some different settings for their audio engines. Usually it allows the sample to be played once, or to be looped, or to be played back and forth, or to be looped and be played back and forth continuously. Tricky term. Resampling. Term resampling is tricky because it has two meanings in audio. First, it can mean shaping a sample with a sampler or any processors and then recording it again, resampling, and then often putting that new sound into a sampler again. But it can also mean the process of sample rate conversion of an audio file. If we're changing the sample rate from 88.2 kHz to 44.1, then this process is also called resampling. So sampling is basically capturing audio and manipulating and playing it as it was an instrument. It gives a lot of possibilities, but also gives some limitations. So if you just sample a single hit of a cymbal, it's going to be really static because every single time the sound's going to be triggered, it's going to be exactly the same. And this is where multi-sampling comes in. This is a technique where you take multiple samples of the same object and then create a patch that can be really playable, so it sounds almost like this instrument. A multi-sample patch always sounds much more natural than a patch based just around one single sample. So I'm gonna sample this right cymbal here. First, I'm just gonna sample one hit and we're gonna see what we can do with that. I'll play it back. The first thing we have to do, and here's an instance of sampler, which is a built-in Ableton's sampler. The very first thing we need to do is to put the sample into the sampler. So as it says, drag sample here. I'm gonna take the sample and put it here. It's being loaded. So as you can see, this is a part of the longer recording, but I've only selected this part where I actually hit the cymbal. It's played back. You'll be able to see that now the audio is going to be played back by the sampler. So the most basic thing you can do with a sampler is you can pitch shift your audio. But first, as it's particularly important as we're working with a percussive sound, we need to make sure that our sample is going to be played back from where I actually hit the cymbal, so there's no silence before. I'll just zoom it in and make sure that the sample starts right before the hit, which is somewhere around here. Let's listen to it now. So rest of the signal flow is much like a subtractive synthesizer. Again, the only difference is the sound source, the very first block of the sound creation process, where in subtractive synthesis obviously that would be oscillators. But here, just instead of those oscillators, you can use any audio. After that, you can use your filter and your envelope to shape the sound. Of course, we can also use LFOs. I'm going to activate this LFO here and assign it to filter. I'll reduce the cutoff of the filter so the effect's going to be audible, because we're adding the volume here on the modulation page. And now we have created this weird effect sound. So this is the power of the sampling. You can turn any audio into something completely different. But for now, let's just stick with a percussive cymbal sample. I'll try to keep it fairly natural. I'll turn off the LFO. I'll open the filter and reduce the resonance of it. So I have now created this simple pattern. It's definitely not too exciting and needs some shaping. I use the main amplifier's envelope to shape the dynamics of this cymbal. I'll close the envelope, play back the loop, and then I'll increase the decay. I'll add some sustain. And maybe try a different filter. And there we have it, a very simple patch made of a sampled ride cymbal. So now you can see how you can create an electronic instrument with any audio using samples. Let's now take some more samples of this ride cymbal and create a multi-sample patch to make it really come alive. Let's see what we can do with these. I've cut them out of the recording and I gave them names. I've called them gong, mid and bell, depending on where do I hit the cymbal. So let's give them a listen. Here's the sound I've created before, and here's the section where we can make multi-sample bell, bell 3. So now we have multiple samples. Let's give it a listen. We need to remove the silence from the beginning of each sample. We have this window here. So we're in a key section where we can adjust which key is going to trigger which sample and the rest of them. So now I actually want this sample to be triggered only by this one key. So I'm gonna adjust it just. I hope you enjoyed that video. Thank you.